Okay, thank you. Can you hear me and can you see my screen?
Yes, you can start.
Okay. Good afternoon, everyone. I'm Irene Pessolano, a PhD researcher with Professor Raffaella at the Mechanical Department in Politecnico di Torino. I'm glad to explain you our work on thermal and electrical characterization of the silicon nitride blanks through active thermography technique for experimental test and numerical simulation. Before going into the detail of the study, let's introduce our framework. We deal with ceramic balls for hybrid bearings. In this frame, the ceramic balls are used thanks to their physical, thermal, and electrical properties to guarantee an high-performance product and safety in their application. In fact, compared to standard bearings with steel balls, they have a higher wear resistance thanks to the higher Young modulus, a larger temperature range due to the higher coefficient of thermal expansion. Ceramic guarantee self-lubrication properties and does not allow the current to flow through bearings, obtaining an electric insulation effect. Those are only some properties of ceramic balls that explain why hybrid bearings are implemented in several fields, such as medical equipment, machine tools, spindle, turbine generators, aircraft, and electrical motors. The major goal of this research is the study of thermal and electrical properties based on the thermal analysis. Therefore, if the active thermography as a non-destructive technique can be applied for the thermal and electrical characterization. In order to fulfill the goal, several steps are necessary, such as the experimental characterization, a microstructural analysis, the active thermography test, and the electric conductivity measurement. Then a numerical approach with a finite element method simulation to extract the thermal conductivity and the heat capacity, and the same is needed for the electrical part. Then we need
I think we have.
Okay. I'm sorry, I lose the connection, but I think that now it's okay.
Okay. Yes.
Okay, I'm sorry. So I was saying that we try to find out the correlation between thermal and electrical parameters. In the present study, we focus on the first two goals in order to get some steps to obtain the major goal. Okay, first of all, let's introduce before the infrared thermographic technique. The thermographic technique can be passive or active. The main difference is related to the external heat source. In passive thermography, there is no external added source, while in active thermography, there is an external heat source that in our case is a laser power. Inside the active thermography technique, we can have the lock-in technique or the pulsed technique. The lock-in technique is a steady-state technique where we have a modulated wave. The energy is concentrated in a frequency value and the penetration depth is related to frequency. While in the pulsed one, it is transient, we have only one impulse or a step loading. The energy is distributed on the frequency range and the penetration depth is related to frequency range. Anyway, the thermal response provides information on the surface and material properties. As a first step in our study, we performed an experimental characterization in order to obtain thermal and electrical parameters. Then the heat transfer multiphysics simulation is performed to extract the thermal conductivity simulation parameter, and then we perform the discussion of our results. The current investigation involved the silicon nitride ceramic balls to measure change in thermal and electrical response. The image shows how the sample was derived from the full ball. In general, the fabrication process for ceramic balls is composed by 3 main steps: the powder synthesis, the powder consolidation, and the ceramic sintering. The investigated samples were characterized by the same powder and blank source, but different process type. In fact, in one is only pressed and sintered, while the other two add another treatment that is called isostatic pressure before sintering, and the hot isostatic pressure after sintering. The experimental characterization include a visual and microstructural analysis in order to find out the microstructural and mechanical process properties used for the FEM simulation. The first analysis conducted was a visual inspection with a 3D digital microscope according to the ISO standard 23277, and no cracks and no macropores were detected. The second study was performed on the material, so the density, the crystal structure, the hardness, and the microstructural parameter were evaluated with appropriate instrument and procedure. The table reports the density, the hardness, and the fracture toughness for the 3 samples. Name is the UCA, UCP, and UCS. Non-destructive active technique is applied for thermal measurements response. The source of external heat is a laser head. The source has a maximum power of 50 watt, and it is triggered to provide a short output pulse to the sample. In the laboratory setup, a mechanical fixture is used to hold the sample. The location of the source on the sample is chosen primarily, and in the present study is of 0.5 meter. The energy dissipation effect after the laser excitation is monitored by a thermocamera. For the experimental test, the input parameters are related to the heat external source. The pulse period expressed in milliseconds, and the laser power expressed as a percentage of the maximum power. The campaigns were conducted following a factorial plan with 2 factors, and each input factor contains 2 levels. This combination leads to a simultaneous study of the factor effect in the process and the interaction of their levels. The table reports the main input parameters. For each sample, 4 tests were conducted. The test plan contemplates 2 tests at low energy and 2 tests at high energy. Therefore, we have 4 testing configurations for each sample and 3 repetitions of experimental tests. Focusing on the thermal response for active thermography technique, we can say that different specimens show similar behavior. The major difference in output response can be detected at high energy level, which means that to point out different thermal features, the high energy level should be better investigated. The graph on the right reports the percentage difference in respect to the UCS sample for the same energy configuration. Again, some evident differences can be detected at high energy level. Moreover, this analysis is conducted only on the maximum temperature and does not consider other important parameters such as the trend slope of the transient. The heat transfer simulation was performed on COMSOL multiphysics software. The Fourier law heat conduction equation were implemented, as you can see in equation 1 and 2, where ρ is the density, Cp the heat capacity, T the temperature, Q the conductive heat flux vector, capital Q the heat source. As a second step, the boundary conditions were set following equation 3, where Q0 is the inward heat flux and H is the heat transfer coefficient. The boundary conditions are set considering that all phases are subjected to natural convection with air, and the loading conditions were reproduced, simulating the heating for the different samples. At the end, as results, we obtain the thermal conductivity and the specific heat. The present slide reports the model calibration for the free sample and the fitting between the experimental and numerical data. The research of the optimized parameter led to excellent results. In fact, the correspondence between the heating and cooling down transient is great. Moreover, the optimized parameter obtained correspond to the experimental one available in literature. Let's move now on the electric conductivity setup. Each specimen has been measured with the voltmeter metered indirect current. A DC test voltage with a B voltage test of 1 kilovolt is used as a stimulus quantity, while the detected response is the current that flows in each specimen. Each specimen under test is placed upon the positive electrode, and on the opposite side of the specimen is electrically connected to the negative electrode, which is guarded by a third electrode that collects leakage current and excludes them from the current measurement path. A shielded cable connects the negative electrode to the ammeter. A spring is mechanically coupled to the negative electrode in order to ensure a proper contact pressure on the specimen. Then the resistivity reported in table were calculated considering the test voltage and the measured current. Sample UCS exhibits the highest resistivity, while sample UCA is the one with the lowest resistivity. As we said at the beginning, one of the goals was trying to correlate the thermal and the electrical parameters. In detail, in the left graph, the maximum temperature over the simulated thermal conductivity is reported, while in the right graph, the electrical over the simulated thermal conductivity. In both cases, we found an apparent correlation. Therefore, in conclusion, this work points out the importance of active thermography as non-destructive technique. In fact, it was possible to provide the thermal transient, both the heating then the cooling down phase, for the 3 different specimens obtained with the 3 different Si3N techniques. For low energy level, the active thermography characterization did not show evident difference between the sample. Then the thermal multiphysics simulation of active thermography testing calibrated with the experimental thermal profile provided the thermal parameter, K and Cp, corresponding to literature data. Last, the maximum temperature on specimen show correlation with thermal and electrical conductivity of the three different specimens. That's everything for our side. I thank you for your attention and we are available for any question.
Okay.